Let's deal with problem number 2 for Lewis structures, even though I love them so much. Number 1, they don't work with certain molecules where the simple bond order just doesn't follow, right? For ozone, that's an example, right? Let's have a look at this one right here. Here's the best we can do with ozone. We draw an internal salt, giving it an overall no net charge, but a very dissatisfying, what looks like positive and negative charge. But that's not horrible. What is a little vexing, however, is that if this structure is true, you'd expect the double bond to be shorter than the single bond. You'd expect a short bond here and a long bond there. You don't see it. Ozone has exactly the same bond lengths. How are we going to fix that? A logical way to do it that they did not go with would have been to assume, well, it's not a single bond there. It's not a double bond there. It's 1.5 bond order for each time. And sometimes you'll see it in textbooks with a line there, and a dotted line, meaning half a bond there. That actually would work just fine. It would imply the linear shape, more or less, I think. But that's not what they went with. They went with something that's a little more complex. Was it a better decision? Well, you can decide. They said, if we can't show it with one structure, let's show it as the average of two structures. These are called resonance structures. They resonate, maybe, or not, depending on what you think. And they move the electrons around. They say another structure might be to take that lone pair, throw it in there to make a double bond, and then take those two electrons and throw it, there it is, throw it up there to make a lone pair there. And that would give you another structure that would look like this. Let's make a couple of points. Number 1, this is not a chemical reaction going on. These double-headed arrows here are specific for resonance and resonance only. This is simply, mankind's attempt, womankind as well, to show you what this one molecule looks like by saying it's the average of two structures. If you're saying yuck, well, maybe that's justified. Once you get deeper into this in organic chemistry, you can see that it's kind of cool the way it can show you things that those little dotted things really might not. But this is what we got. This is a resonance structure. This at least does two things. It says it's the average of those two structures. So we're between no charge and negative charge here. We're between positive charge. Oh, we're always positively charged there. Isn't that interesting? And we are not quite negatively charged there. But more importantly, it's a 1.5 bond order throughout, giving us a equal bond lengths. Let's try to do the same thing with the nitrate anion. Once you get in the habit of this, you may enjoy this electron flow process, drawing those arrows. And so what we'd like to do is show two other equivalent structures here, since the nitrogen to oxygen bonds for this, as you might have guessed, are all identical. Let's take that electron pair, throw it in there, and we've got overabundance of electrons here, so we're going to take those pair of electrons that form that bond and form an extra lone pair. You should see no charge there, no change in charge there because it's both gaining and losing electrons, and 3 lone pairs there giving us our negative charge. We'll do the same thing here, throwing it onto there, and then show our third resonance structure. That's 2 different forms of the nitrate anion. I don't think we showed the third. And here's, I believe this is laughing gas, N2O. Now, the way it's drawn, we should be able to do what they call delocalize, meaning spread out those electrons. Let's take that electron pair, go into there, and that electron pair that forms the bond, and go to there. And can you see what we're doing? Can you see how there's no positive charge change on that nitrogen right there? And that's the equivalent resonance structure with an interesting triple bond right there. These are known as resonance structures, and they're an important part of organic chemistry. Between formal charge and resonance structures, we attempt to alleviate the limitations of Lewis bond structures.